Hi, my name is Lucas and I'm going to talk to you a little bit about my thesis project, Dissipation and Decoherence for Generic Open Quantum Systems. First, what is an open quantum system and why should we care? Well, because no real physical system is truly isolated and thus will be influenced by its environment. The idealization of a closed system is an extremely useful one, but it fails in several situations. For instance, if you want to study an atom, you could say your system is that atom only. But it's not alone in the universe. In fact, it's surrounded by many other atoms and also by a bath of radiation, and they greatly influence our atom of interest. Many experimental techniques and quantum technologies like the laser rely on this kind of system, so we have a practical interest in open quantum systems. But they are also crucial on a more fundamental level, namely for the conceptual understanding of the act of quantum measurement. Measuring the system by definition makes it an open system. We also know that in quantum mechanics, a measurement act influences the measurement result itself, so we really need a theory of open quantum systems for a thorough understanding of the process of quantum measurement. I have been talking about the importance and the interest of open quantum systems, but what are the differences between open and closed systems? The state of a system will be a superposition of many different quantum states, each having its own phase. In a closed system, these phases only oscillate, and the phases of different states have definite relations at all times. We then say that their evolution is coherent. By the way, quantum coherence is fundamental for quantum computation, so if you want to build a working quantum computer, you should really study all this. For an open system, its coupling to the environment causes coherence to decay in time. The system is thus basically losing quantum information into the surroundings. Because different states couple differently to the environment, the phases also randomize. As a result, the system starts losing its quantum behavior. Quantum decoherence is an extremely fast process for macroscopic objects, and this is why it's so hard to see quantum phenomena in our macroscopic world. There is also quantum dissipation, where the system is losing energy into the environment. If the bath is large enough, this process is irreversible. We have by now addressed every word in the title, except for generic. For that, we have first to understand how we can describe an open quantum system. In general, a complete microscopic description for all degrees of freedom of both the system and its environment is impossible. Even if we could obtain such a description, it would be useless, because it would contain much more information than we are interested in. We want to know what the energy of the system is, or if a metal will conduct, or if an atom will spontaneously emit, not the quantum state of each and every particle in the system. So, what we do is to look for an approximate or effective description for the degrees of freedom of the system only. One possibility is that of Lindbladian dynamics. In this approach, we describe the evolution of the system using the Lindblad equation. Let me guide you through it. All the objects in this equation are matrices, which are basically arrays of numbers we organize in a particular way. The density matrix ρ is what specifies the state of the system. Its entries are the different probabilities for the system to be in each of its states. Then we have the Hamiltonian H, whose entries are related to the energy levels of the states and their interactions. Finally, we have a set of jump operators L. The entries tell us how the system couples to the environment and how fast decay processes occur. Finding exact solutions for this equation is very hard. What people have been doing for a long time now is to find special solutions for what are called integrable systems. These are systems where many matrices are zero or very symmetric. We could say they are simple enough to allow an exact solution. But we can also think of the opposite limit. If the system and the interaction with the environment are really complex, then we can expect that the tiny details won't really matter, and the only thing that survives our effective description is an average behavior. That's exactly what we mean by generic open quantum system. We will forget all microscopic details and focus only on the universal behavior. We are thus seeking a statistical, that is random theory for open quantum systems. But we saw that the formulation of the problem is full of matrices, so we'll use a tool called random matrix theory. Basically, we say that the entries of these matrices are random variables and try to extract the relevant information about dissipation decoherence from them. The good thing is that random matrix theory has been developed tremendously over the years and has many different working tools. However, it has been mainly applied to closed quantum systems, and up until very recently, no one tried to apply it to Lindblad dynamics. So that's exactly what I'll do for my thesis. I hope I could get you at least a little bit as excited as I am, and thank you for watching.